In this section, we're going to be looking at derivatives of logarithmic functions, logarithms being the inverse of exponential functions, and they also come up quite frequently in business and economic applications. So we want to know how to take the derivatives of those types of functions, okay? Now, if we take a look at what's in the book here, let's see. It's got to load for just a second. Okay, so here we can see the definition of derivatives of both the natural log of x, natural logarithm is the inverse of e to the x, and also the natural log of a function itself. Okay, so basically what these two things are saying in our definition is that if we have a function that's the natural logarithm of x, then the derivative of that function is 1 over x, provided that x is greater than 0. Because the domain of the original function, natural log of x, is only defined when x is greater than 0. And also you'll notice here, if x were equal to 0, we would get an undefined derivative. Okay, so we do need our x to be greater than 0, but that's how we find the derivative of a natural log. It's just defined as 1 over the argument. This thing here, the thing that we're taking the natural logarithm of, that's called the argument. So if we want to take the derivative of the natural log of the argument of x, that's 1 over x. The second definition in that box is actually just a consequence of the chain rule. It says if we want to take, if we have the natural logarithm of a function of x as the argument, so not just x, but an actual function of x, then that would be 1 over the argument, just like our above definition. But since the argument is a function itself, we have to use the chain rule to multiply by that function's derivative. And then just tidying that up a bit, we get g prime of x over g of x. Okay, and that is that second definition inside the box in the book is this piece here. Okay, so again, that's just coming from applying the chain rule to the first derivative definition for the natural logarithm, assuming that our argument is in and of itself a function. Okay, so let's take a look at an example. Let's say we want to find f prime of x if f of x is equal to the natural log of 4x cubed minus 17x plus 6. Okay, so this is what we want to find. Well, according to our definition above, when we are finding the derivative of a natural logarithm, that derivative is equal to 1 over whatever the argument was. And in this case, here is our argument, 4x cubed minus 17x plus 6. But now because that argument in this case is a function, we have to use the chain rule to multiply by the derivative of that function, which in this case, we would bring the 3 down in front. 3 times 4 would be 12. X to the 3, and then we'd subtract 1 from the power. 3 minus 1 would be 2. Minus 17, because the derivative of negative 17x is negative 17. And then the derivative of positive 6, being a constant, would just be 0. And then tidying this up a little, we could rewrite this as 12x squared minus 17 over 4x cubed minus 17x plus 6. And that would be our derivative. Okay, if this factored nicely and there was a common factor that we could pull out, to make it look more tidy, we could absolutely do that. In this case, it doesn't factor nicely. There's no common factors to pull out, so we can just leave the derivative in this form.